Okay. Shall we start? Anyway, I'm recording. Even if they are 5 minutes late, also Abhi can join. Rohit also is not responding, and Steve has messaged that he can join. I don't know why he is doing like that. I really don't. Okay. All of you have finished solid state in the school, is it?
Yes, auntie.
Bharadwaj, you
Yes, and in my school also they finished.
finished. Rishi
Yes, ma'am. Finished, ma'am.
finished. Okay. Okay. Then it will be a revision for you then. It will definitely be a revision for you. You are able to see the board today, Rupa? Is it better? Board?
Auntie, the board is clear, but I know if you write anything.
Okay. Wait. I will just get one.
Hey, what were you telling, Auntie?
I'll just erase it neatly so that then if I write, I think it will be more clear. Okay. Now I think it is more clear.
Hey, today, okay, I am not saying anything.
Tell me, Bharadwaj.
No, Auntie, I was supposed to say video was very clear, Auntie.
Video is clear. That I'm happy to know that video is clear. Always there is some problem with the video. Now, kids, you have been studying about the 3 different states of matter. Since your childhood, you have been studying about the 3 different states of matter. What are they? Solids, liquids,
Liquids and
gases. Now, how do you say that a substance is solid or a liquid or a gas?
If the
Yeah,
substance is rigid, it is solid.
That means if you go to the basic level, here the we say that constituent particles, because it can be an ion, atom or a molecule. Ion, atom or a molecule. The constituent particles are closely packed. They are closely packed, and why they are closely packed? Because they have a lot of intermolecular forces of attraction between them. Okay, so basically why is the difference? In solids, the particles are very closely packed. Okay, here and intermolecular attractions are very high. Here they are not as closely packed as solids, but they are not as apart as gases also. They are in between. Slightly closely packed. Whereas in molecules, gases, last year we have studied in kinetic theory of gas states of matter, gases, that each molecule behaves as if the other molecules do not exist at all. Okay, absolutely. The kinetic theory of gases, one of the postulate is that there are no intermolecular forces of attraction or repulsion among the molecules. Like that they behave. Okay, so that is the basic difference. So what happens, because they are closely packed, intermolecular distances are very small. Interparticular particle distances are very small. Here they have little freedom. Here there is a lot of freedom. Okay, so since the intermolecular distances are very small, as a result, what happens, this point is important. They are very closely packed and they are fixed in their positions. They occupy fixed positions. Here they do occupy fixed position, but they can move a little bit. Whereas here, absolutely, they don't have any fixed position at all. They are absolutely free. So, because of all these properties, solids have very important, important characteristics. What are the characteristics of solids? See, gases you have studied in 11th. Liquids we are studying, like about liquids little bit we studied, fluids we just studied little bit about viscosity and all we studied, but most of it is solution means studying about the properties of, wait, Abhi kya join? Abhi. So we have studied about the properties of gases in 11th. We are studying the properties of liquids in solutions. Now we will study the properties of solids, little bit, very small. Actually solid state is a very big branch. It is common to physics, and solid state physics is also there, solid state chemistry is also there. It's a very big branch actually. The new research is all in solid state only, most of the research. So we are going to, you are just introduced to them. You will know as you go on, you will know how much the depth of the chapter here. So because the atoms, I don't say atoms, because the constituent particles are closely packed, intermolecular distances are very small, intermolecular attractions are very high, they occupy fixed position. Because they occupy fixed positions, they do not have the freedom of movement. Okay, they do not have the freedom of movement. So they can only oscillate in their mean positions. There are so many different types of movements like stretching, bending, vibrating, translational, rotational, all the movement. That is the intrinsic sum of all the energies only, we call it as internal energy. That is what is internal energy we talk about in thermodynamics. Okay, so solids, they can only oscillate in the mean position, that's all. They don't have too much of freedom. Okay, so they are fixed. Because of all these, they have certain characteristics. What are they? They are rigid, they have high density. High density means mass by volume is high. Okay, you know, little amount of mercury or lead, it weighs so much, volume will be very small, but mass will be very high, so density will be very high. So they have high density, and you know that gases can be compressed to any volume because the intermolecular spaces are so high, distances are so high that they can be compressed to any small volume. We have studied that in pressure correction, volume correction, van der Waals equation, everything. So whereas liquids also cannot be compressed, not to that extent. Solids though, they cannot be compressed at all. So incompressibility, and very important, definite shape and volume. Definite shape and volume. So what are the characteristics of solids? They are characterized by rigidity, high density, incompressibility, and definite shape and volume. All these are characteristics of solids. Okay, and because they occupy certain fixed positions, now we will confine our study to solids. We will not study about liquids and gases. So we will study about solids. Now when we say solids, because they are confined to the fixed positions, they have a regular pattern of arrangement. You can study where that one particle is present in space. We can study that. Okay, so they are orderly arranged, we say. They are orderly arranged. But is the order continuous? Is it present throughout the solid? That is a question mark. So the order, that is the pattern, regular pattern of arrangement, can be to a particular region or in bits and pieces in small regions, or the order can be throughout the solid. Based on the nature of the order, solids are classified into two types. One, crystalline solids and amorphous solids. Crystalline solids and amorphous solids. So, in crystalline solids, as the name itself says, the arrangement of atoms is, they have a regular pattern of arrangement throughout the solid. Whereas in amorphous solids, what happens is that the arrangement is there. There is a pattern, but the pattern is not maintained throughout the solid. It is in bits and pieces. Okay, it is haphazard. Amorphous itself means haphazard. It is not arranged through, it is not throughout. Okay. So, because they have a regular arrangement of particles throughout, what are the characteristics of that? Crystalline solids, they have high melting point. They have high melting point. That means not high, I can say sharp melting point. They melt at a particular temperature. Whereas amorphous solids, they do not melt at a particular temperature. They start melting like plastic. They start melting. Slowly it will melt. It will melt. You cannot say at this temperature it melted. So they will melt over a range of temperature. Over a range of temperature it will melt. Amorphous solids. Example for amorphous solids will be plastic, rubber, glass. All these are amorphous solids. Okay. Whereas crystalline solids, example will be any metal or any salt. Any salt will be a crystalline solid. Okay. So they have sharp melting point. You can say it melted at a particular temperature. The whole thing will melt at a particular. I think they will show you the melting point also in the lab. There is an experiment to show the melting point and boiling point. That's the basic experiment we have in 11th. So they melt at a particular temperature, whereas they melt over a range of temperature. Now, next is the in crystalline solids, when you cut, you can cut, they will undergo a clean cleavage. You can cut it sharply at a point. It will undergo clean cleavage. Whereas here when you cut, they do not undergo clean cleavage. They will give pieces of irregular shape. Okay, irregular shape. Okay, and they have definite shape and volume. They have definite shape, whereas these do not have definite shape. You can give any shape to them. They do not have definite shape. And they have very high heats of fusion. Enthalpy of fusion. What is enthalpy of fusion? It is the temperature required to convert 1 mole of a solid to liquid. Liquid to gas is vaporization. So they have definite enthalpy of fusion, whereas they do not have definite enthalpy. That is, the energy required to melt is also not measurable, not constant. Whereas here it is constant. And crystalline solids, they are called true solids. They are called true solids, whereas amorphous solids are called pseudo solids or supercooled liquids. Actually, glass is a supercooled liquid. They have asked in the question, they have asked. What happens? Glass in old buildings, that is the in-text question you have. In old buildings, what happens? Because glass is a supercooled liquid, the window panes, they flow down. The bottom one will become thicker than the upper part. Because it's a liquid, it will melt like that, and it will float. Okay, that shows that it is a supercooled liquid. It is not a true solid. And whenever they ask any difference, you will have to write the example, like sodium chloride or any metal or anything.
Auntie, what's the third point, Auntie, under crystalline solid?
Third point is they you can cut them with a knife. They will.
Okay.
Whereas here
It will be irregular.
they get
Okay.
into pieces. If you break a glass,
Okay,
you
Andy,
will
got it.
get all that pieces. Nowadays you get glass so that you don't have sharp edges in the glass. Okay. Now another very important point is that, see, for example, you have positive, negative, positive, negative, positive. You have a regular pattern of arrangement of particles in this. They are called as anisotropic. That means if you measure, see, if you measure physical properties like refractive index, thermal expansion, electrical conductivity, in this direction it will be different, in this direction it will be different. If you measure diagonally, it will be different. It will be different. So they are different in different directions. Whereas here they are called isotropic. Iso means same. The physical properties, if you measure, they are same throughout the solid. Okay. So solids, that is also one question is asked. Solids in which the physical properties are not different in different directions, they are crystalline solids, anisotropic and isotropic. Whereas amorphous solids are isotropic. If you measure them, it will be same in all the directions. Okay, these are the differences of between crystal. They can ask in any like different form. You should know the subject. I'll send you the notes. You should know the subject properly, but it need not be asked like give the directly. It give the differences between crystalline solids and amorphous solids. No. I will tell you how differently they have asked. Then you will know how can it be asked. But you should know each and every point. You should be clear. Okay, each and every point. Now in this chapter we are more interested in crystalline solids because we are more interested in studying their structures. So we are more interested in crystalline solids. Very interesting to study the crystalline. I'll tell you how many different types of all that is there. You will wonder. Okay, really you will wonder. It is such a big chapter actually. Now, when I say crystalline solid, now crystalline solids, as I told you, the constituent particles can be an ion, atom or molecule, anything like that. Based on the nature of the constituent particles, crystalline solids are classified as 4 types. They are classified as 4 types. 1. Molecular crystal, ionic solid, molecular solid, ionic solid, metallic solid and covalent or network solid, network crystal. These are the 4 different types of crystals. What are they? Molecular solid crystal, ionic crystal, metallic crystal and covalent crystal. Now, what are the differences between the, as the name itself says, here the constituent particles are neutral atoms like atoms of inert gases or molecules. Okay, see, molecular crystals are again classified into 3. Molecular solids are again classified into 3. 1. Non-polar molecular solids, polar molecular solids and hydrogen bonded molecular solids. Okay, so molecular solids are again classified as non-polar, polar or hydrogen bonded. Now when you come to non-polar molecular solids, if you don't understand, wherever you want to, you can stop me. Non-polar molecular solids, here the constituent particles are atoms of inert gases like helium or argon, or the molecules formed by covalent bond formed by non-polar molecules. For example, non-polar means solid hydrogen. Rohit has done. 2 minutes. Rohit has done. Good, right, you joined. So, their non-polar molecular solids means here the constituent particles they are non-polar. Non-polar means what? The bond should be between the same type of atoms, or dipole moment should be zero. Dipole moment should be zero. For example, solid hydrogen or solid carbon dioxide. Carbon dioxide has got zero dipole moment because it is carbon is at the center, double bond O. So that the carbon dioxide molecule is having zero dipole moment. Then the question is, how are they bound together? What is the force that binds them together? Here what happens in non-polar molecular solid, what happens is that momentarily a dipole is developed in a molecule. Momentarily it will come across something, there will be a charge distribution in the molecule, and that momentary dipole will induce dipole in the other molecule. Here the attraction is between momentary dipole and induced dipole, we say. All these different types you have studied in 11th actually. You start theory of states, kinetic theory of gases with this actually. So here the attractive force is between momentary dipole, a dipole formed at a moment. Okay, there will be some charge distribution that will induce dipole in the neighboring molecule, and they are bound together. That's all. They will stay together like that. So that is the binding force, and these are very weak. They are called as dispersion forces or London forces, and they are very weak. So they have got very weak van der Waals forces, dispersion forces between them. And characteristics of these are, the non-polar molecules are very soft. They are very soft. Generally, their liquids or gases at room temperature. Okay, they are very soft and they are very high volatile. They are very volatile. They have got low melting point and boiling point. And they are non-conductors of electricity, either in the solid state or in the liquid state. They are non-conductors of electricity, and they have got low enthalpy of vaporization. Enthalpy of vaporization is from liquid to gas. Energy required to convert 1 mole of a liquid to gas, that is enthalpy of vaporization, that is very, very low. Even at room temperature they will exist as gas. Okay, so that is about non-polar molecular solids. Now, polar molecular solids means molecules have a dipole. For example, HCl or solid sulfur dioxide, solid ammonia. All these, they have a dipole, permanent dipole. HCl is a polar covalent molecule. So one end, positive end will attract the negative end of the other molecule. So that will hold them together. That is dipole interaction will hold them together. That is the force of attraction, binding force in them. But molecular solids, even polar molecular solids, they are also soft, they are also volatile, they also have very low melting point, and they also have very low enthalpy of fusion, but little better than non-polar. Non-polar have the least, then you have polar molecular solids. They are better than them, little better than them. Okay, example will be HCl, sulfur dioxide or ammonia. Now, hydrogen bonded molecular solids, how are they? You know that if you when you in a molecule, hydrogen is linked to more electronegative and small size like fluorine, oxygen or nitrogen, that will undergo hydrogen bonding. They will form hydrogen end of one molecule, will form a hydrogen bond with the negative end of the other molecule. Okay, so that is called as hydrogen bonded molecule. So here they are held by strong hydrogen bonds. Strong hydrogen bonds. So, but they are also they also have, they are better than these two. Okay, they have little high melting point. They are also non-conductors of electricity, and they are also volatile. But the boiling point and melting point are little higher than these two types, molecular solids of the other two types. They are little better than that because of the strong force of attraction between them, hydrogen bonding. That is why water is a liquid. Otherwise, water would have been a gas at room temperature. Because of the hydrogen bonding, water is a liquid. So, that means what? Water is having a very high boiling point actually. Compared to its structure, it is having a very high boiling point. So, these are the characteristics of hydrogen bonded molecular solids. Now, coming to ionic solids. As the name itself says, what is an ion? Ion is a charged species with either excess or deficient of electrons. So, in an ionic solids, you will have positive ions and negative ions. It can be like 1 positive, 1 negative, or 1 positive, 2 negative, or 2 positive, 1 negative. It can be any ratio, but you will have positive and negative ions. They are the constituent particles, and they have constituent particles are positive and negative ions, and they are held together by strong Coulombic force of attraction, electrostatic forces of attraction. There is a strong bond in them. Because of the strong bond, they have high melting point. They have high melting point. They are hard and brittle. They are hard and brittle, and they do not conduct all these. Each point is important. They do not conduct electricity in the solid state because ions are not free to move. Though ions carry current, but ions are not free to move in the solid state. But when you melt it or put it in water, they conduct electricity. So, they conduct electricity only in the molten state, fused state, or when put it in water, aqueous state. And they are soluble in polar solvents, and they are slightly or insoluble in non-polar solvents. And they have high enthalpy of vaporization. They have high enthalpy of vaporization. These are the characteristics of ionic solids. What are the characteristics? The constituent particles are positive and negative ions present throughout the molecule. They are arranged in a regular order throughout the solid. Now, they are held together by strong interionic forces of attraction, Coulombic forces. Because of that, they have high melting point. They are hard and brittle, and they are non-conductors in the solid state. Ions are not free to move. They conduct only when put it in water or in the molten state. And they are soluble in polar solvents, but they are very slightly or insoluble in non-polar solvents like benzene, carbon tetrachloride, all that. And they have high enthalpy of vaporization. This is about ionic solids. Now, coming to metallic solids. What is a metallic? This is a very, very interesting and very important type of bonding. Actually, I think you study in 11th metallic bonding. I think they have removed it now. Oh yeah. We used to teach this as a separate chapter. Now what happens is that in metallic solids, metals, you know that all metals, they have very low enthalpy of ionization. They want to lose electrons readily. So they lose electrons, and metals will form M plus or M2 plus M3 plus, whatever it is. Aluminium will form 3 plus. One atom of aluminium will lose 3 electrons. Okay, and one copper will lose 2, or one sodium will lose 1 electron. So in a metal, what happens is that you have positive core, that they are called as kernels. Positive core, that is called as kernels, and you have kernels and like this, and you have electrons throughout. It's a very strong bond because all electrons attract all positive ions. Electrons are freely moving. Okay, here the constituent particles are kernels and all these 1 mark question. The constituent particles are kernels and mobile electrons. The electrons are completely mobile. Okay, they are free to move. So, we say that it is called as electron sea model only. In a sea of electrons, they are very mobile. Because of that mobility, they have got they induce lot of properties. Okay, this bond itself is called as metallic bond. It's a special kind of a bond. Each atom donates one or more electrons to that sea of electrons. Okay, it will lose one or more electrons and it will give it to the sea of electrons. Okay, so because of this, metals have very important characteristics. Metals have varied properties. Okay, metals have varied properties. They can be soft as well as hard. You know that mercury is a liquid at room temperature, whereas iron, platinum, they are all very hard. Okay, so they can be hard as well as soft. And the metals have another very important property is that they are very good conductors of heat and electricity because of the mobile electrons. When you pass heat, the electrons carry that heat. When you pass electric field, the electrons carry that electric current. So they are very good conductors of heat and electricity. And they have got that metallic luster because when light falls on them, the electrons absorb that energy, go to a higher energy state. When they come back, they emit energy. So they have that color. Okay, they have that luster and color that we are going to little discuss in coordination compounds. So metals have that metallic luster and color in some cases. And very important is that, see, when you press them, when you deform them, the positive ions, they adjust in such a way that it is like a smooth covering of electrons. They will immediately adjust themselves. That is why they are malleable and ductile. They can be drawn into sheet and wires, pressed into sheets and wires because they do. It is like this. The positions of positive ions can be adjusted immediately. Okay, they can adjust it. You can mold them into sheets and wires because of this form of the model. Okay, they get deformed, but you can adjust them. And metals also have high heat of vaporization. Okay, those are the properties of metallic solids. And covalent solids, they are also called as network solids. Why they are called network solid is that here the constituent particles are atoms. You imagine diamond. Okay, that is best way of knowing about covalent. Even carborundum, silicon carbide, quartz, all these, graphite. Graphite is also a covalent crystal. So all these, in these, the atoms are held together by, there is a continuous network of covalent bonds throughout the solid. And covalent bonds are very strong and they are directional in nature. And that is why atoms are fixed to their positions. They are held, they are very strong. You know carborundum, that is silicon carbide or diamond, how strong they are. And they have got very high melting point. In fact, they even decompose before melting. That much high melting point. Very high melting point. They have a continuous network of atoms throughout the crystal. Covalent. That is why they are called as, they form a three-dimensional giant structure. They are called as giant molecules. Big molecules because of that structure. And they are non-conductors of electricity. Okay. And they have very high melting point, and except graphite, remember this, except graphite, though graphite is a covalent solid, covalent crystal, graphite has got sp2 hybridization. See, they will ask you this. You know that in um, 2p4, correct. This is carbon. Okay. In carbon, what happens? Wait. 2s2, 2p2, no? Boron carbon, yes. 2s2, 2p2. Actually, it will be like this in carbon. So, it can, one electron, if it jumps, it can undergo sp3 hybridization, sp2 or sp. If it undergoes sp3 hybridization, all are involved. All of them bonds like diamond.
Auntie, can you repeat, Auntie?
See, carbon can undergo sp3 hybridization, sp2 and sp. So, if it undergoes sp3 hybridization, it will be like diamond. It will be very hard and no electron is free. It doesn't conduct. Okay, it doesn't conduct. Whereas graphite, it will undergo sp2 hybridization. One electron is free. Because of that one electron is free, graphite has a totally different characteristic compared to other covalent solids. It is soft, it is layered. Graphite is layered and it will conduct. Graphite is a good conductor because we use graphite anode in so many reactions in metallurgical processes. So graphite conducts because it is sp2 hybridization. And sp is acetylene. They will ask you to arrange. Many times they have asked, every year probably. They will ask this sp3, sp2, sp. Diamond they will give graphite and acetylene. Or they can give you the bond angle, or they can give you the shape, or they can give you the hybridization. In any one of the form, definite question this is. Okay, so they will have different characteristics because of the difference in the hybridization. Except graphite, all the covalent solids or network solids are bad conductors of electricity. Only graphite is a good conductor of electricity. So this is about the different types of solids you are going to study. You are studying. Okay, so now what we will do is you have the textbook or a rough sheet or anything like that. You first take the textbook, all of you. Take the textbook and Abik, you have the textbook?
I have to open a PDF from internet.
Oh, you have to open PDF. Is it? You don't have the physical textbook.
No, Auntie, it's actually kind of very much, the text
Okay.
is not proper.
Okay, then I will discuss it anyway. And in the notes, everything is written neatly. Even the in-text questions are written neatly. So, answer the questions now. Whatever we have learned, you will answer the questions now. Okay. So, first, Bharadwaj, why are solids rigid? Why are they rigid?
The 1 minute, Auntie, I just opened my.
Why are solids rigid?
They have a strong intermolecular attraction with them.
So, what will happen? First, for rigidity, you start that they are closely packed. They are closely packed.
Yes.
Intermolecular distances are small. Okay, and they occupy
lack
fixed
of,
positions.
mobility.
That's very important. They occupy fixed positions. They are not able to move.
Yes,
Okay, they can only
yes,
oscillate.
Auntie, they do not flow.
They can only oscillate in their about their mean position. That is why they are rigid. You have to write like that. Okay.
Okay.
Solids have a definite volume. Krupa. Why do solids have a definite volume? Nice. Where is the noise? Oh, okay. Oh, there. Okay.
Auntie, it's because this thing, the particles vibrate around fixed locations, auntie.
They are fixed. They are fixed in their positions. They are not able to move about. That is why they're rigid. So they have a definite volume. Okay. Now,
Yes, auntie.
classify the following. Correct. Classify the following as amorphous or crystalline. You will have to classify now. Either amorphous or crystalline. Okay. Rishi, polyurethane. Polyurethane.
Ma'am?
Polyurethane. You have to classify it as either amorphous or crystalline. Polyurethane is a type of plastic.
So amorphous, auntie.
So it is amorphous.
Auntie, how will we know with the name, Auntie, which solid it is?
Normally, if it is a polymer, it will be a plastic.
Oh, okay.
Okay, so polyurethane is a plastic.
So amorphous, no, Auntie.
Amorphous. It is amorphous. It is actually carbamate. You don't have to know the structure. It becomes too much. Just leave it. Naphthalene.
Ma'am, after it, crystalline, sorry.
Naphthalene has got a definite structure. 2 benzene rings. It's a crystalline solid. Benzoic acid. If they have a proper structure, it will be crystalline. Benzoic acid structure, you know, C6H5COOH. It has a definite structure.
So it's a crystalline
Crystalline.
solid.
It is crystalline. Teflon. Teflon
Amorphous.
is a polymer.
Amorphous.
Teflon
Amorphous.
is a polymer. Polymer means it is a plastic. Teflon is the coating which we have that non-stick. Teflon. So it is a
Amorphous.
amorphous. Potassium nitrate.
No, crystalline.
Crystalline. Cellophane.
Amorphous.
Amorphous, auntie.
Amorphous. It is from plant. Cellophane. Then polyvinyl chloride. PVC.
Ma'am, amorphous.
Amorphous. Fiberglass.
That's also amorphous.
Amorphous. Copper. Copper is a metal. So it will have a different.
Crystalline.
We are going to study the structure of copper also. Sodium, copper, everything. Next question. Why is glass considered a supercooled liquid? Why glass is considered...
It's because it's an amorphous solid, auntie.
Yes, it's an amorphous solid. So, what will happen? Like liquids, it will flow. But very slowly. Not like liquids.
Yes, and it has a tendency to flow, but it won't like flow.
Yes. So, how do you prove this? You can see the window panes of old buildings which are thicker at the bottom than at the top. That means glass has flown. This shows that it flows down. It's a supercooled liquid. Now, next question. Refractive index of a solid is observed to have the same value along all directions. Comment on the nature of this solid. Would it show cleavage properly? Refractive index is same throughout.
Auntie,
If it is same throughout, it is amorphous. Correct. If it is same through, see, crystalline solids, I told you, they have a regular pattern. So if you measure it diagonally or along the different lines, it will be different. Whereas amorphous solid, they have the same property, same refractive index throughout. So if you say refractive index is same throughout, it is amorphous. If it is amorphous, will it show cleavage properly?
No, aunty.
No, it will not show cleavage properly. Okay, I'll give you all the answers. You have to write the notes neatly. Okay. Okay. So then, now again, classify the following solids in different categories based on the nature of intermolecular forces operating in them. That means now you have to write the intermolecular, classify them based on the intermolecular, like whether it is ionic crystal, molecular crystal, covalent crystal, like that. You will have to write. Potassium sulfate. Potassium sulfate.
It's an ionic solid, no, aunty.
Ionic, correct. Tin,
Tin should be metallic solid.
metallic. Benzene.
Benzene should be covalent, no, aunty.
Benzene is molecular non-polar. Non-polar molecular solid.
Okay.
Because benzene, though there is a network, as you say, but the network is not throughout.
Okay.
Discrete molecules.
Yes.
Okay, actual force is between the molecules only. It is non-polar molecular solid. Urea.
Covalent, aunty.
Urea is also a, urea is NH2CONH2. NH2CONH2. It is having a polarity. Urea is having a polarity. It is a molecular crystal, polar molecular crystal. I'll repeat again everything. You will just listen to me. Ammonia. Ammonia.
Covalent again, aunty.
Ammonia, I told you, it is a hydrogen bonded molecular crystal. Ammonia, water, all these are hydrogen bonded molecular crystals.
So
Are
molecule.
linked by hydrogen bonds. Okay? I repeat, I'll just repeat, you just listen. Zinc sulfide. Zinc sulfide is an ionic solid having zinc ions and sulfide ions. We are going to learn the structure of zinc sulfide later. Okay, zinc sulfide. Graphite.
Network, aunty.
Yes, graphite is a covalent crystal or network. Rubidium. Rubidium. It's an alkali metal.
Metallic solid.
Metal. Argon. Argon. I gave the example.
Molecular solids, aunty.
Molecular non-polar.
Non-polar.
Silicon carbide. Carborundum. It is carborundum. It is a very, very strong, hard substance. It is a covalent crystal like diamond. Very hard it is, silicon carbide.
Okay.
Okay, it is called carborundum. So, I repeat, potassium sulfate, ionic, potassium and sulfate ions, tin, metallic, benzene, molecular, non-polar, urea, molecular, polar, ammonia, water, both hydrogen bonded, molecular solids, ammonia, water, zinc sulfide, again crystalline, graphite, network, that is covalent, rubidium, metallic, argon, molecular non-polar, silicon carbide, network, covalent crystal. Okay, see, covalent crystal normally diamond, silicon carbide, graphite. These three only are asked. Okay. Now, next question. Solid A, some solid, it is a very hard electrical insulator in solid state as well as in the molten state. It's an electrical insulator in solid as well as in the molten state and melts at extremely high temperature. What type of solid is it?
Auntie, can you repeat, Auntie?
I repeat, solid A, some solid, is a very hard electrical insulator in solid as well as in the molten state and melts at extremely high temperature. See, when I say very hard, it cannot be a molecular solid.
Coal and solid, Auntie?
Yeah, ruled out. And when I say electrical insulator, it is ruled out that both in the solid as well as in the molten state. So you rule out both ionic and metallic. And melts at extremely high temperature, it has to be covalent. When I say hard, you rule out molecular. When I say electrical insulator in solid as well as molten state, you rule out ionic and metallic. Only left is covalent. Melts at extremely high temperature. What type of solid is it? It is covalent or network solid. That is the, like that question they will give you. One mark question will be like that. So if you know the characteristics properly, you can know the type of the crystal. Okay. Next question. Ionic solids conduct electricity in molten state but not in solid state. Explain.
And in molten state, they can move freely, Auntie. But in solid state, they can't.
Correct. In solid state, they will have a regular geometrical shape. Ions are fixed in their positions. They cannot move. But when you melt them, they are free to move. So they can carry current. So they conduct electricity in the solid state because of the free movement. Okay. So in the solid state, they have got electrostatic force of attraction which will not allow them to move. What type of solids are electrical conductors, malleable and ductile?
Metallic.
Metallic. Malleable and ductile will be correct. Malleable and ductile will be metallic. Okay. So because if you do it also, they can arrange immediately themselves because they have got the cushion of electrons. The positive ions can arrange themselves neatly. They can be drawn into wires and get it into.
Auntie, except metallic, everything is insulators, no, Auntie.
Ionic, when you put it in water or molten state, that they have to. But in the solid state, only metals are good conductors. Correct. As you say, only metals are very good conductors. Okay. And conductivity varies. Metals have varied properties. That is why we use metals so much. Metals have varied properties. Actually, if you study metallurgy, you can study different properties of metals. Okay. So I will give you the answers for all these. You can just write that in this one, and they have given it in the table, in the form of table also. Even in the textbook also they have given it neatly. You can just go through that also. No problem. They have given in the textbook also neatly they have given. Okay. Among covalent crystals, only graphite is soft and it is a conductor. Exception. You have to remember this. Exceptions only you have to remember. Graphite is soft and it is a conductor, whereas all others are hard and insulators. Okay. They have given nicely in the table, in the form of a table. They have given nicely in the book also. They have given this table. They have given. You just learn the table. Whatever we have learned now, they have given it in the form of a proper table.
Yes.
You can just learn that. Okay. Now, shall we proceed? I'll just and then stop. Anyway,
Yes.
I'll send you the note. If you write, it will take double the class. If you have to write all the questions, answers, notes, everything, it will take more time. But I'll send you the notes neatly written. You can just copy it You can complete the notes along with in-text and example, everything. But here also you will have problems. Okay, lot of problems, and I'll tell you, solid state they can make it very, very tough. I'm not scaring you, that's the fact. They can make it, I'll tell you how difficult it can be. As you go, as you proceed, I'll tell you how difficult it can be and how are the different types of questions I've seen. Okay, so be prepared for a very tough question from solid state. So learn, I will be teaching definitely more than what is there in the textbook. So you keep one notebook or scribbling pad or sheets where you will work out problems. In between only we will work out. You keep that, and you can just put it, keep that along with the notes, so that you will writing part will be reduced. Problems you need not write. We will work out the problems in that. Okay. So I'll just do little more, and then I know it's not possible to listen to continuously. You can listen, but I'll tell you how much you can take it. Don't worry. Okay. Now we will learn about the crystalline solid structure of them in detail. But it's very interesting actually. Solid stuff. Now you are able to see the board.
Yes, and it is clear.
It is clear. Anyway, I will erase it with this one also, so that the board becomes more. The duster itself is having lot of dust. That is the. Okay, this is better. Now the interesting part. This is all the basic part, like introduction part, like, okay. Actual crystal you will study now. Actual crystal structure you will study now. Now, you know that there are three types of axes. Okay, X, Y, Z. Correct? However, they are all the three are perpendicular to each other. You can just say anything like that. Now, if you have a solid or a crystal, if the constituent particles are arranged in space throughout the crystal, you know that there is a regular arrangement of in space. What I mean is in all the three axes. Space means three axes, X, Y, Z axis. If the crystal solid has a regular pattern of particles, arrangement of particles in all the three axes, you call it as a space lattice. Lattice means just the arrangement. Okay, so in space, if they are arranged neatly, you call it as space lattice. Okay, they can be arranged in so many different types. I will tell you the different types of arrangements. Okay, so when you have the different types of arrangements, the particles will occupy a fixed position. The particles will occupy a fixed position. That fixed position, particle means atom, ion or molecules, that you call it as lattice point or lattice site. Lattice point or lattice site. What do you mean by a lattice point? It is the position where you can find the particle. That's it. Each lattice point will be having one particular particle. Okay, and if you join them by imaginary lines, there are no lines in the crystal, absolutely no, but we draw the lines to know the shape of the crystal. To know the shape of the crystal, we draw the lines. It will give you the geometry of the crystal. It will result.
What is lattice lines and lattice point?
Lattice point means the positions of the particles. You call it
Okay.
or lattice site.
Okay.
And each lattice point means there is a particle there. It will have a particle. And lattice points can be joined by an imaginary line to give the geometry of the molecule. It will bring about the geometry of the crystal. Okay. So, now this is about space lattice, and is that like our body consists of so many fundamental particles called cells, and so many cells will form tissues, muscles, like that. Even the crystal will have a basic one unit which will repeat itself in all the three directions. It will bring about the crystal. That basic unit, which when expanded, repeated in all the three different directions, will result in units. It will give you the crystal. You call it as unit cell. What do you mean by a unit cell? Unit cell is the fundamental unit which when repeated in all the three axes, which result in the crystal, proper crystal. Okay, it is the smallest. That is, should take a crystal, keep on cutting it, you will end up with the smallest unit. That unit you call it as the unit cell. It is the fundamental unit, and it will, like our atom. Atom when repeated, you will get the so many elements or compounds, everything like that. When you repeat it, you will get the crystal. Okay, and very important, unit cell will have three parameters. What are the three parameters? Okay, these are the three axes. So parameters are axial length and axial angles. This you must know. This is this is the basic of crystal structure. Axial length and axial angles. What are they? This along the x-axis, this length you call it as A. This you call it as A. I will tell you how you have to learn. You learn like that only. This you call it as B, and this you call it as C. A, B, C. And like this. The angle between B and C is alpha. Angle between C and A is beta. Angle between A and B is gamma. So, axial lengths are A, B, C, and axial angles are alpha, beta, gamma. So, different types of lattices are formed when there is a difference in all these A, B, C, and alpha, beta, gamma. If you have different lengths and angles, you will get different crystals. Okay, you will get different crystals. Now, you will study now. You will study the. See, actually, crystals are classified, or unit cells are classified as two. One, primitive unit cell, and non-primitive unit cell. Non-primitive unit cell. Unit cell is classified into two types: primitive unit cell and non-primitive unit cell. What do you mean by that? What do you mean by that is, if I say primitive unit cell, you will have the lattice points or the constituent particles only at, see, they are not joined like this. We are joining to know the shape. So you will have the particles only at the corners. Primitive means they have particles only at the corners of these. Okay, sorry, I forgot to. For example, if I take a cubic system, they will have only at the corners, you call it as primitive unit cell. What do you mean by non-primitive unit cell? Non-primitive unit cell will be, you can have particles at the edges. Okay? See, you will have, I'll just write the crystal, then you will. I'll write different crystals, and then you will have the cube. I'll show for cubic, then I'll tell you for other structures. Because this is the basic. If you understand this, you can understand the chapter nicely. Okay, so you will have non-primitive unit cells, means they are also called as, I will tell you why they are called like that. Non-primitive unit cell, apart from the corners, apart from the corners, you will have a particle. It can be a particle one at the center of the unit cell. That is called as body centered unit cell. Body centered unit cell, BCC. That you call it as body centered unit cell. Or you can have particles apart from the corners. You can have particles present at the center of each face. Each face means front, back, up, bottom, sides. That is called as face centered unit cell. That is called as FCC. Or apart from the corners, if you have the particle at the center of two faces, okay, you have center of two opposite faces, that is either top bottom or sides or front back, any two, only two, that is called as end centered. End centered. So unit cells basically are of two types, primitive and non-primitive. Non-primitive is also called as centered because they are present at the centers. Extra particles are present at the centers. So primitive means only at the corners. Okay, that is the basic unit cell. For example, cubic if you take, you will have only at the 8 corners of like this. Now, non-primitive, that is centered, are of 3 types. One, they can be body-centered cubic, that is apart from the corners you will have a one particle at the body center, that is like cesium chloride. You will have one particle at the body center. Or face-centered, you know that it will have 6 faces. A cube will have 6 faces. I have one cube, I'll show you. It will have 6 faces. So apart from the corners, if you have a particle at the center of each face, you call it as face-centered cubic cell, unit cell. And end-centered means apart from the corners, if you have particles at the center of two opposite faces, only two, top bottom or sides or front back. Okay, if you have that, you call it as end centered unit cell. So you will have 3 types of non-primitive and you will have one primitive unit cell. Okay, so if you slowly study the crystals, we find that there are 7 types of crystal systems. There are 7 types of crystal systems. This is very, very important. 7 types of crystal systems are present. How they are formed? They are formed based on whether the axial angles and lengths are same or different. They are same or different. I have written all of them actually. I have written all the 14 Brevis lattices. I'll show you how to write that. Okay, so 7 crystal systems. This is very important. You have to know this. Students get confused here only, and properly they ask this only in depth. So how to remember that? All of you take a sheet of paper and write along with me. Write along. I'll tell you how to write. Okay. Now you write first column system. What is the system you are studying? Axial length, axial angle, and few examples. Okay. So how you will learn is, like, just see how I write. You write C T O T H M T. First write like this. C T O T H M T. Then what is C? Cubic. What is T? Tetragonal. Tetragonal. What is O? Orthorhombic. Orthorhombic. What is T? Trigonal. What is H? Hexagonal. Yeah, what is M? Monoclinic. What is T? Triclinic. There are 3 T's here. Remember to write them properly. See, first is cubic, then is TE, that is E comes first. You write it as tetragonal. Then orthorhombic, and then write trigonal, TR, it comes later. Hexagonal, monoclinic, triclinic, cut the last. You will definitely remember triclinic. I'll tell you why. You will definitely remember triclinic properly. There is absolutely no problem in that. Okay. This trigonal is also called as rhombohedral. Orthorhombic. Trigonal is also called as rhombohedral. Some books they have given it as rhombohedral. So you can write it like this. Okay. So trigonal is also called as rhombohedral, or you can write it as trigonal. So cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, triclinic. Will you remember this? CT, OT, HMT. Okay? All of you will remember this? Kids?
Yes, auntie.
Okay. Now, I will tell you how to write this. They will ask this only. I will tell you how to write this. You write A equal to B equal to C. A equal to B not equal to C. A not equal to B not equal to C. Cubic, you write A equal to B equal to C. Tetragonal, A equal to B not equal to C. Orthorhombic, A not equal to B not equal to C. Again you repeat that. A equal to B equal to C. A equal to B not equal to C. A not equal to B not equal to C. Repeat again. And triclinic, A not equal to B not equal to C. Okay. Now, axial angle. How will you remember axial angle? Here you write first for the first 3, alpha, beta, gamma equal to 90. All the 3, alpha, beta, gamma equal to 90. Alpha, beta, gamma equal to 90. Okay, write like that much. Last triclinic, you write alpha not equal to beta, not equal to gamma, not equal to 90. You write it off that first. First 3, you write alpha, beta, gamma 90. For all the 3, you write. Last one, alpha, beta, gamma not equal to 90, you write. Fourth one, alpha equal to beta, alpha equal to beta, equal to gamma, gamma not equal to 90 degrees. Alpha, beta, gamma, they are all equal, but they are not equal to 90. Whereas in triclinic, nothing is equal and they are not equal to 90 also. That's what it means. Okay. In hexagonal, alpha, beta 90 degrees, gamma equal to 120 degrees. Alpha, beta 90, gamma 120. Whereas in monoclinic, alpha, gamma 90 degrees, not equal to beta. Beta is not 90. It will be little different from 90. Okay. I repeat how to remember this easily. CT, OT, HMT. Cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, triclinic. How will you write the axial length? A equal to B equal to C. A equal to B not equal to C. A not equal to B not equal to C. Repeat that. A equal to B equal to C, A equal to B not equal to C, A not equal to B not equal to C, and triclinic definitely A not equal to B not equal to C. You write that much. Okay? Axial angle. How will you remember? Alpha, beta, gamma 90 for first three. First three alpha, beta, gamma 90. Last one alpha not equal to beta, not equal to gamma, not equal to 90. You write that first. 4 are over. Now, fourth one, trigonal, alpha, beta, gamma, they are all equal, but they are not equal to 90. But they are all equal, but not equal to 90. Hexagonal, alpha, beta, 90, gamma, 120. This you can remember because graphite you can remember. That is 120 angle you can remember easily. If you remember graphite, you will know that it is 120. Gamma, 120. And monoclinic, alpha, gamma, 90, but beta is not 90. Beta is not 90. And if you observe this, they will ask you 1 mark. They can ask you this also. That will be the difficult question. Like they can ask you what are the axial length and angle. Or they can ask you which is the most symmetrical. Which is the most symmetrical? Which is the most symmetrical?
Auntie, the one which has everything 90 degrees.
Everything equal. That is cubic.
Yes, auntie.
A equal to B equal to C, alpha, beta, gamma 90. Most unsymmetrical is triclinic. Nothing is equal. Okay. So cubic again will have 3. Simple cubic, body centered, face centered. Tetragonal will have 2. All of them will have simple. That is primitive at the corners. Definitely all of them will have. Okay. Triclinic, hexagonal and trigonal, they have only primitive. Only one. But cubic has got 3. Primitive, body centered, face centered. Tetragonal, again primitive and body centered. And orthorhombic has got the highest. It has got simple, face centered, end centered, body centered. All the 4. If they ask you which has got the highest number of crystal lattices, it is the orthorhombic. It has got simple, body centered, end centered, face centered. Trigonal, hexagonal, triclinic, only one. Primitive only. Okay. And monoclinic also you will have end centered and simple. I have written all the crystal systems here. It's very interesting to write, and you know what, it is difficult to show the angle not equal to 90. Equal to 90 it is easy to show. Not equal to 90 it is difficult to show. Somehow it will form like that only. But I have tried to write the different shapes. It was interesting for me to learn all the. See, all these 7 crystal system will give rise to 14 brevis. That is what I said, no, face centered, body centered, all that. If you add everything, you will get 14. It was discovered by a scientist by name Brevis. It is called as brevis or brevis, whatever it is. Brevis, brevis lattices. There are 14 brevis lattices. Okay, orthorhombic 4, cubic 3, all that I told, no, tetragonal 2, all that. If you add all that, you will get 14. If you are interested, they have given it in the books. All the structures they have given neatly, you can learn. And most important thing you have to learn here is the examples. Examples you have to learn. I will tell you how to simplify the example. See, triclinic, you remember copper sulfate, 5H2O and K2Cr2O7. K2Cr2O7. Okay? And monoclinic, Na2SO4, 10H2O, PbCrO4. This will come only by practice. There is no easy way to remember this. For cubic, no, you remember NaCl. NaCl, KCl, diamond, all these are cubic. And for tetragonal, tin oxide, titanium oxide, barium sulfate, no, calcium sulfate, barium sulfate is next, calcium sulfate. Okay, now for orthorhombic, potassium nitrate, potassium sulfate, barium sulfate, all that. Hexagonal is very easy actually. Mercury, sulfide, ice, graphite, all these you can write hexagonal. Ice, graphite, and all the metals. And for this sodium nitrate, calcium carbonate. Here lead carbonate you can write. See, you and in sodium nitrate, calcium carbonate, you can remember the nitrogen family, that is arsenic, antimony, bismuth. Sodium nitrate, along with that trigonal, you remember nitrogen family, arsenic, antimony, bismuth, they all form that. Okay, and they've asked this one, KMNO4, very important. They have asked this. KMNO4, potassium permanganate is trigonal. Potassium dichromate is triclinic. Don't get confused. They will ask this. Trigonal and triclinic. Triclinic is dichromate. Trigonal is permanganate.
Okay.
Okay. So you remember as much as possible, and metals and some of the ionic solids we are studying in detail the structure. So definitely you will remember. How
Okay.
also you will remember. That is also there in the textbook. I'll teach you that neatly. So some metals and ionic solids you will definitely remember how they are arranged, everything. Only these examples are a bit challenging for you to remember. You make sorry, was some network problem. So you make your own way of remembering few examples, at least few examples you do, but definitely learn axial length and axial angles. Okay, is it easy to remember axial length and angles? Krupa, Bharadwaj, Rishi, Rohit.
Andy, can you hear me?
Yeah, I didn't hear anyone's voice.
Yes, and your video got stuck, Andy.
Is it easier to remember now?
Yes, Andy, it's easy.
It's easy, no? Krupa? Krupa? Yes. Rishi? Rohit? Why I am not able to hear anyone's noise, or they are not talking, I don't know. Or there is some problem with their mic. Oh, my video is breaking, is it? Okay. Rishi?
Andy, did you hear me when I talked?
No, I am not able to hear anyone's noise actually. Voice. Rohit?
Ma'am, I can hear you, ma'am. Your voice is breaking on that.
Breaking, yes. You are able to learn, and Rishi?
Yes, ma'am.
Oh, my audio is also erratic. Okay, my God. Okay. So this is easiest way to learn the lengths and angles. If you are thorough with this, you have learnt really good amount of solid state. So what you do today only, you make the table, write 2-3 times along with few examples. You will learn. Is that clear?
Yes, ma'am.
Okay.
Yes, Andy.
Okay, I'll send you the notes. Probably I'll try sending the notes. Okay. Otherwise, you have written the table. No, you learn the table thoroughly. Thoroughly you learn. Any question asked, you should be able to write. Okay? Okay, kids. We'll continue in the next class. I'll send you the notes. Then you can just copy that. Okay?
Thank you, ma'am.
Auntie, what time, Auntie, next class?
Pardon?
Auntie, what time, Auntie, next class? I thought
Next
school is
class,
there.
tell me. Shall I message in the group?
Okay, Auntie.
Okay, I'll message in the group. Okay? Okay, bye.
Bye, Auntie.